I think we can. Okay. Okay, so today's lecture will be about modular forms of level 1. We're going to be interested in holomorphic functions on the extended upper half plane, complex valued holomorphic functions. So I need to tell you a little bit about what it means to be holomorphic on the extended upper half plane. In the case of level 1, it's relatively easy. In the case of higher level, it requires a little bit more fine-tuning, which I will do in the next lecture. But for now, essentially, we know what it means for a function to be holomorphic in the usual upper half plane. So what does it mean for the function to be holomorphic at infinity, which is the extra point that you've added? And all the cusps are equivalent for SL2Z. So we're looking at holomorphic functions which transform in the following way. For all A, B, C, D in SL2Z. So these are called modular forms. These are modular forms. These are modular forms of weight k, the k here being so what does it mean for something to be holomorphic at infinity? Well, the basic neighborhoods of I infinity are of the form u sub c, z in the upper half plane, with the imaginary part of z bigger than c. These are your basic neighborhoods. And if we look at the map that sends z to q, which is e to the 2 pi I z, notice I use the letter q here. You can see that this transforms u sub c. It sends u sub c to the unit disk, punctured unit disk, so punctured unit disk of radius e to the minus pi c, e to the minus 2 pi c. So you have this punctured disk without the origin, and we're saying that the function is holomorphic at infinity translates to saying that the function is holomorphic in this thing, including 0. So as such, it's a holomorphic function in the neighborhood of 0 under this mapping, and so it has a Laurent expansion. So we end up getting a Laurent expansion, or actually a Laurent expansion of this function, which will look something like, because it's holomorphic, it has to start at 0. It'll look like a sub n q to the n under this mapping q. So this is what we will call the Fourier series of f at I infinity. So we can talk about the Fourier expansion of the function at infinity. Notice, by the way, here the element 1, 1, 0, 1, the translation element, is an element in SL2Z, and because we're looking at functions which transform in this fashion, that translates as f of z plus 1 is equal to f of z. Therefore, the Fourier expansion is not surprising, and sometimes we write this in this fashion. And sometimes we call these a sub n's are called the Fourier coefficients of f at infinity. So here, since I'm dealing with the full modular group, I'm looking at functions on the upper half plane, extended upper half plane, which transform in this fashion for all elements of the full modular group, and all the cusps are equivalent under this full modular group. Therefore, you only have one non-inequivalent cusp, and so you only need to worry about what it means to be holomorphic at that one cusp. Okay, so we have that. We define the order of F at I infinity to be the smallest n for which a sub n is not 0, to be the infimum of all the n such that a sub n is not 0. For any other point in the upper half plane, the order, by the way, so we'll denote this denoted v sub I infinity of f. For any other point, we define v sub z of f to be the order of f at z. In other words, let's say z naught. In other words, when I think of the function f as a function of a complex variable, it's holomorphic at z naught, therefore it has a Laurent expansion, and therefore it begins with some first non-zero term, has a certain 0 of order v sub z naught of f. That's all I'm saying. So this is the order of f at z naught. So for all the points now, we've managed to define the concept of order for any point in the extended upper half plane. So we say that f vanishes at infinity. F vanishes at the cusp I infinity if v sub I infinity of f is bigger than or equal to 1. So the formal definition then is a modular form of weight k for SL2Z is a holomorphic function f on the extended upper half plane, which is complex valued, satisfying f of az plus b over cz plus d equals cz plus d to the k f of z for all a, b, c, d. So this is the definition of a modular form. One could think of essentially the theory of modular forms as a generalization of the theory of Fourier series.
Is it difficult to read from the back?
Oh, is it difficult to read from the back? Did you want me to write bigger? Okay. You know, there's lots of space here. Yeah, I think you should come to the first two, 3 rows. I mean, or even you can sit on the stage if you like. All right. Now notice that if I take 2 modular forms and one more definition before I continue. We say f is a cusp form if f vanishes at all the cusps. Remember, the cusps were those extra points that I added to get the extended upper half plane. In the case of SL2Z, there's only one inequivalent cusp. So in that case, you only need to check infinity. But in the case of higher levels, you may have to check the behavior at other cusps. So here's a little bit of notation which makes it convenient for later use. So here's an exercise which can probably be done in the afternoon. Let gamma be ABCD in GL2 plus R, and Z in the upper half plane. Define J of gamma Z to be CZ plus D. So gamma is this matrix ABCD, so the C and D are here, and we will denote by J of gamma Z, CZ plus D. Then show that J of gamma 1, gamma 2 acting on Z is J of gamma 1, gamma 2Z, J of gamma 2Z. And then we'll introduce this so-called slash notation. We will take a modular form or take any object and slash sub gamma of Z is defined to be determinant of gamma to the power k over 2, J of gamma Z minus k f of gamma Z. So if gamma is in SL2Z, of course, this is 1. But if gamma is in GL2 plus R, there will be a non-trivial factor here. We'll just use this as a notation. And so to say that F is a modular form is for SL2Z is equivalent to saying that F slash gamma equals F for all gamma in SL2Z. That's a nice convenient notation. And then the advantage of the slash notation is you have this property, which I'll leave also as an exercise for you to do, which is an easy consequence of the previous exercise, and that is that F slash gamma 1, gamma 2 can be, so exercise F slash gamma 1, gamma 2 is equal to slashing with gamma 1 first and then slashing with gamma 2. And here's one more exercise. Suppose F is a holomorphic function. Is holomorphic, and F of Z plus 1 equals F of Z, and F of minus 1 over Z is equal to Z to the K F of Z. Then F is a modular form of weight K for the full modular group. And I'll just give you a small hint on how to do this. This is telling us that F slash T, the translation operator, is F. And this second property is telling that F slash S, that, S was that matrix 0, 1, minus 1, 0. Sorry. 0, minus 1, 1, 0. It was this matrix, and T was the translation matrix. So in our slash notation, we find that f slash t is f and f slash s is f. Therefore, f slash the group generated by s and t is f. But the group generated by s and t is a full modular group. So this is how you essentially do that. All right. Now we'll consider the vector space of modular forms of weight k. Notice that if I have two functions that satisfy this rule, then if I add them, I still get a modular form. If I multiply by the scalar, I still get a modular form. So we have the vector space m sub k of SL2Z, the C vector space of modular forms. And inside this thing, we have a subspace of cusp forms C vector space of cusp forms of weight k. By the way, with respect to the slash notation, in some books, people use f slash subscript k to denote this k dependence. But if it's clear that there's only one k floating around, you might as well do this. If there are a couple of k's floating around, then it might make sense to put that in. All right. Now I'd like to study the structure of these vector spaces. That's the goal of today's talk. We'd like to study these. Notice that if f is in mk1, sometimes I'll just drop the SL2Z there. If f is in mk1 of SL2Z and g is in mk2, then fg is in mk1. Okay. We have this kind of structure. The same applies for if f is a cusp form and g is a modular form, then the product fg is again a cusp form. That's because if f already vanishes at infinity, you don't care what happens at g as long as it's holomorphic. F times g certainly vanishes again at infinity, therefore you have this property. Okay. Now, an interesting exercise that you can do is to show that mk of SL2Z is just the zero space for k odd. In other words, when k is odd, we have no non-trivial modular forms. All right. So let's construct explicitly some modular forms. So these were first constructed by Eisenstein. But before I do that, let me just make some general remarks about quadratic forms. So if I have a positive definite quadratic form, so this is a positive definite quadratic form, binary quadratic form. Binary meaning there are two variables. And to say it's positive definite is equivalent to saying that A is positive and the discriminant AC minus B squared is also positive. And we can write our quadratic form in matrix notation. Might make it a little bit easier to see. We can write, we have the row vector mn, the 2 by 2 matrix A, B, B, C, and so this is equal to AM squared plus BMN plus CN squared. So you can write this number in matrix notation, and we make the observation that the matrix here is a symmetric, real symmetric matrix. And from your basic linear algebra, you know that you can always diagonalize a real symmetric matrix by an orthogonal transformation. So we can diagonalize the matrix by an orthogonal transformation. Remember what an orthogonal transformation is. It's a matrix P such that PP transposes the identity element. So P. So that means, in other words, we have the following: P A B B C. P transpose is a diagonal matrix. This orthogonal transformation also preserves norms. So P being an orthogonal transformation, P preserves norms. Or lengths of the vector. So you have this. Therefore, if we put UV equal to PMN, if we make that change of variable, so here's my quadratic form, and I'm going to make this change of variable UV equals P times MN, then you can see that this column vector MN can be written as P inverse times UV, but P inverse is P transpose. That's the orthogonal transformation. So I get P transpose, so I can rewrite my quadratic form QMN in terms of U and V, and when I do that, you get so I'm writing this as P transpose UV. And so you can see that this is going to become A, B, B, C, and Mn is P transpose, so this is P transpose UV. And the transpose of this would be UV times P. So you get this product of matrices. And now we know that this guy here is the diagonal matrix lambda 1, lambda 2, and therefore this becomes nothing but lambda 1 u squared plus lambda 2 v squared. So you get this nice, very nice thing. And so because the matrix is non-singular, the eigenvalues are not 0, and so this is at least lambda u squared plus v squared, where lambda is the minimum of lambda 1, lambda 2, and it's not 0, it's actually positive. So you have, it's positive because it's a positive definite quadratic form. That's why the eigenvalues are positive. So you have this, but u squared plus v squared is the norm of the vector uv, and uv is the vector obtained by transforming mn via p, and because p is a transformation that preserves lengths, the length of uv is the same as the length of mn. So this is equal to lambda m squared plus n squared. So this is just a general remark, has nothing to do with modular forms. It's essentially linear algebra. And I just want to use this in the study of Eisenstein series, so I just thought I'd review it for you. Okay. So we now define for k bigger than 2, gk of z to be this double series. So we go over all integers m and n, so that simultaneously they're not 0. We have mz plus n to the power k. So this is what's called the Eisenstein series. Z is the upper half plane. And I'm going to leave the question of convergence as an exercise. You will need to use this observation to study convergence. Using our observation, earlier, it is easy to see, easy to show, gk of z converges as a series for k bigger than 2. And by the way, I'm only going to deal with positive integers for the sake of this course. So we're always talking about, so k is, I told you that there were no modular forms of weight, odd weight. So essentially the first non-trivial case is k equals 4. So it's easy to show that this is convergent. And using the Weierstrass M test, which I hope you remember from your complex analysis class, using the Weierstrass M test, gk of z is an analytic function in the upper half plane. And the question is, what happens when I try to calculate gk of az plus b over cz plus d with a and b, c and d in SL2z? When you try to calculate this, you find that I will substitute for z az plus b over cz plus d, and then do the obvious. You will get a cz plus d in the numerator outside, and then you will get summation 1 over whatever it is. So let's just quickly do this. Az plus b over cz plus d plus n. So you end up getting m a plus n c z plus plus what? Plus mb plus nd all to the power k. And it's a small exercise for you to show, because A and AC are relatively prime. Remember, AD minus BC is 1. So AC are relatively prime, and B and D are relatively prime. So as M and N run through all the integers, so do these. And then you just have to check that they're not simultaneously 0. I mean, one of them could be 0, but they're not simultaneously 0. That would mean that Mn itself had to be 0, because ABCD is an invertible transformation. Okay, so it's a small exercise. So here's an explicit construction for this. So this series now is equal to Cz plus D to the power k times gk of z. So indeed, we've constructed with our bare hands modular forms of weight k. What is the behavior of this modular form at infinity? How does it, I mean, for everything in the upper half plane, it's okay. What happens at infinity? Well, when I plug in z equals I infinity here, 1 over infinity is 0. So the only way this can survive is if m is 0. If m is 0, and of course n should not be 0. And so it's not a big deal to see that gk of I infinity is 2 times zeta k, where zeta is the Riemann zeta function. This is the Dirichlet series representation for zeta of s for a real part s bigger than 1. It'll make its appearance on many occasions in this course, so might as well introduce it now. So you have a special value of the Riemann zeta function as the value of the Eisenstein series at infinity. Okay. Now I'd like to ask what is the Fourier expansion of g sub k of z at infinity. And in order to do this, I will require some knowledge from complex analysis, which you hopefully have seen. One of the things I'll need is this product expansion for sine pi z. So hopefully you've seen this somewhere in life. And if we take logarithmic derivatives, we get, well, if you differentiate, take log and differentiate, you get the cotangent. So pi cotangent pi z is equal to 1 over z plus summation n going from 1 to infinity, 1 over z plus n plus 1 over z minus n. So we write this in so that it's easy to see that it converges if you group this in this fashion. It may be convenient to write this also as summation n in z, 1 over z plus n. Although when you write it like that, then issue of convergence is something to think about. And the way we would think about that is if you pair up n and minus n together, like we're doing here, then and understand that convention, that certainly makes sense. Okay. So if we look at this, on the other hand, pi times cotangent pi z is equal to pi times, well, what's cotangent? We can write that in terms of the exponential function. So I just rewrote, that's cos pi z over sine pi z. I just rewrote that in terms of the exponential function. And I can rewrite this as pi I q plus 1 divided by q minus 1, where q is e to the 2 pi I z. So if we write it neatly like that, then you can see that I can rewrite this as q minus 1 plus 2, so that's 1 plus 2 over q minus 1. Oh, sorry, 2 pi I. Oh, there's a minus sign. So it's q minus, I'm writing it as q minus 1 plus 2, right? Oh, it's a plus sign. So this is equal to pi I plus 2 pi I, or minus 2 pi I, over 1 minus q. And keeping in mind that z is in the upper half plane, mod q is less than 1, and therefore I can expand this as a power series in q. Oh, there's no 2 pi. Yeah, thank you. Yeah. All right, so we have that. And now, so we have that pi times cotangent pi z has this Q expansion. Okay? So if I make successive differentiation of both sides, I get what's called Lipshitz's formula. So Lipshitz's formula. So if I take the kth derivative of this, I'm going to get 1 over z plus n to the k. So we have summation 1 over z plus n to the power k, n in z is equal to minus 2 pi I to the k over k minus 1 factorial, summation n going from 1 to infinity, n to the k minus 1, q to the n. So when I successively differentiate q to the n with respect to z, I keep up picking up powers of n. And so when I do that, you end up getting this. So it's a rather beautiful formula in its own right. And what is the advantage of this? Well, the advantage is that this allows us, this formula, to derive the Fourier expansion of gk of z, and the theorem is for all k bigger than or equal to 4, gk of z is equal to 2 times zeta k plus 2 times minus 2 pi I to the power k over k minus 1 factorial, summation n going from 1 to infinity, sigma sub k minus 1 of n q to the n, where sigma sub k, where sigma sub s of n is just simply d divides n, d to the power s. So this is the q expansion. So q, as always, is e to the 2 pi I. So this is the Fourier expansion of the Eisenstein series. And we get this from the Lipschitz formula in the following way. Differentiate that thing, and that's why we get it, right? I mean, so I've got this formula here, which is pi cotangent pi z. I differentiate it k times, and each time I get some power of n. On the other hand, I'm recognizing pi times cotangent pi z as this, and I differentiate each one term by term, and then you can see that you get that. Okay. So, I mean, it's not a big deal to see this. So indeed, so the proof indeed we have this, and so you can start off by first removing the m equals 0 term from the picture. So we do that. When we do that, you end up getting 2 zeta k, m not equal to 0. Like so. And now I want to analyze this. I analyze it. So m not 0 and n is an integer. So in the fact that I can take this as m going from 1 to infinity and just double it, and then I have a summation over n in z, 1 over mz plus n to the power k. So now the inside sum is set up so that I can apply the Lipschitz formula with z replaced by mz. And when I do that, you can see that this has a q expansion 2 times m going from 1 to infinity of, well, that. So there's this minus 2 pi I k over k minus 1 factorial that kind of comes out. Summation n to the k minus 1 q to the m n, where n is going from 1 to infinity. Okay? So now we group together the exponents where mn equals, let's say, r, and you see that the coefficient that you accumulate in this fashion is, so let's say it's r going to 1 to infinity, q to the r, and the inside sum will be those numbers n to the k minus 1 such that m equals r. That's the same as saying n divides r, n to the power k minus 1. That's precisely the divisor function that I've put on the board at the top over there. So that's basically the how you derive the Fourier expansion. Now, perhaps Karamdev can do the following exercises in the afternoon, and that is, I'm hoping that people have seen the sine pi z product expansion before in life, and that they have derived at least some special values of the Riemann zeta function as an application of that product formula. So I'm going to leave this as an exercise. X over e to the k x minus 1 is the generating function for the Bernoulli numbers. So these b sub k's are called Bernoulli numbers. For example, b0 is 1, b1 is minus a half, b sub 2 is 1 over 6, and usually the b sub 2k plus 1s are all 0 for k at least 1. So b3, b5, etc. are all 0. So you have this rather elementary fact, and the reason I'm introducing it is because you can show using that product expansion for the sine function that 2 zeta 2k is simply 2 pi I to the power 2k, b sub 2k divided by 2k factorial. So if you've never seen this before, well, you're seeing it now. The point here is that these numbers, b sub k's, are all rational numbers. That's clear from the expansion of e to the x, right? E to the x is an expansion with Taylor series with rational coefficients. And so if I do the long division, you're going to get rational numbers as coefficients. So these are rational numbers. This is a rational number. So essentially it's telling you that zeta 2k is a power of pi to the 2k times a rational number. Okay, so when you unravel that, here, when k is an even number, I have zeta 2k here, and I have pi to the 2k here, and essentially the bottom line is I can normalize my series. So gkz is having this value at infinity. I'm going to normalize this in such a way that it has the value 1 at infinity. And so define ek of z to be gk of z divided by 2 zeta k. So that's a scalar multiple of a modular form of weight k, therefore it's still a modular form, but it has the property now that it's 1 at infinity. And because it's 1 at infinity, I just have to check what is the coefficient that goes here, and if I put all this information that I've gathered here together, you find that this actually has a Q expansion, which is very simple looking. So Ek of z is a modular form of weight k So k is always even. And it has the Q expansion, Fourier expansion, given by sigma k minus 1 of n q to the n. So all these factorials and powers of pi disappear, and you have this rather neat-looking expression for your Fourier expansion. This, by the way, is a starting point for the theory of p-adic modular forms, but we won't go into that here. So as examples, let me write a few down. E4 of z is equal to 1 plus 240 summation sigma 3 of n q to the n. E6 of z, 1 minus 504 What is important to notice is that the coefficients of the Fourier expansion are all integers. E8 of z is 1 plus 480 E10 So these are all these generalized divisor functions, and if you think that these are all going to be integer coefficients, there's a nice surprise at E12. E12 of z is 1 plus 65520 over 691 summation n going from 1 to infinity sigma of 11 of n q to the n. So E12 does not have integer Fourier coefficients, but the denominator is a single prime, so it's almost integers except for one prime. And E14, I might as well write this down, E14 is again neatly behaved. It's 1 minus 24 summation n going from 1 to infinity sigma sub 13 of n q to the n. So you have all these Eisenstein series. They have very neat Q expansions, Fourier expansions. And the structure theorem that I'd like to focus on today is how to use these Eisenstein series to determine the structure of the space of modular forms. So notice that the way I've normalized it, ek of z has the value 1 at infinity. And so if you give me a modular form, I ask myself, what is the value at infinity? Let's say it's lambda. So take a modular form and find out its value at infinity. Modular form of weight k. So f has weight k. Subtract this at infinity, and this now vanishes at infinity, and so must be a cusp form. And so this leads you to see that the space of modular forms is isomorphic to a direct sum of the one-dimensional space generated by the Eisenstein series of weight k and the space of cusp forms. Notice that E sub 4 is weight 4, E sub 6 is weight 6, so E sub 4 cubed is weight 12. E sub 6 squared is also weight 12. Since I have explicit Fourier expansions here, and I know the value at infinity is 1 here, and the value here is 1 at infinity, therefore this difference at infinity is 0. Okay? And so the question is, what is the next coefficient in that Q expansion. So it's got to start off at something times Q plus something Q squared, so on and so forth. Well, what is that? It turns out to be 1728. So most of you may know the 1729 story of Ramanujan, right? This is actually where it's coming from. 1728 is the number that you need to divide this by in order to have the lead coefficient to be 1. And this is what's called the Ramanujan cusp form. So this is a cusp form because it vanishes at infinity. This is what's called Ramanujan's cusp form. And it's weight 12 modular form. And in fact, we'll see in a second, this is the first non-trivial example of a cusp form. From this particular expression, it isn't clear that the coefficients of this Q expansion are integers, but they are. Okay? Turns out that delta has a Q expansion given by Ramanujan's expansion, tau, when these are tau integers. And this is often called the Ramanujan function. I'll talk about this in detail in the next lecture. But for now, I just wanted to point this out, and the fact that later we will show that delta of z is actually a product So later we'll show this. This kind of ties up with my first lecture where I was talking about Q expansions and products of this type. This is not a trivial fact to show, but it's a very cute thing to show. Okay, now we will derive what's called the Valence Formula. It's basically a theorem right out of complex analysis, the Valence Formula. And this formula basically says that if you have, let F be a modular form of weight k, not identically zero, then, so here we are in our fundamental domain. I just want to point this out. So let me kind of talk about, before I write this down, maybe I should have said something about orders of zeros and structure of the thing. So here we have these points that we have identified, so-called elliptic points, rho and rho squared I. So we have, this is our standard fundamental domain, and since f of az plus b over cz plus d is cz plus d to the k f of z, we see that if f of z naught is 0, so is f of az naught plus b over cz naught plus d. So in other words, if z naught is 0, is a 0 of f, so is any SL2Z translate of that. So in order to study the zeros of a modular form, it suffices to study the zeros in the fundamental domain. Because if I identify all the zeros of the modular form will be all the SL2Z translates of that particular zero. So that's why we'll focus on the fundamental domain. So focusing on the fundamental domain, we have this formula, fi infinity of f plus 1/2 bi of f. I is the square root minus 1 plus 1/3 v rho of f plus all the other zeros, 0 orders, oh, here in my notation I've got rho squared. Okay, so let's keep rho squared. It'll come out in the wash because the way I'm going to do the integration. Because notice, by the way, rho squared and rho are equivalent. These 2 points are equivalent, so it doesn't really matter which one I use. This is equal to k over 12. So this is the Valence formula. It's actually very easy to prove, and let's just do it. It's essentially a few lines. But out of it will come the entire theory of modular forms. It's a pity I have to rub this off. Yeah, because if I have a 0 of f, then so is SL2Z translate a 0 because if it's vanished, because this is not going to be 0. Because z is in the upper half plane, c and d are integers. So if I'm trying to study zeros, I only need to look at SL2Z inequivalent classes of zeros. Because any two zeros, once I have a 0, any SL2Z translate is that. Therefore, up to translations by the action of SL2Z, I should identify all the zeros. Yeah? Okay. So to prove this, first point is that, first assume, so in order to do this, I want to count the zeros. So let's first assume that, so proof, first assume f has no zeros on the boundary of the fundamental domain. So it means I'm going to assume that there are no zeros on these vertical lines, this vertical line, this circular arc, and this vertical line. So no zeros on that. And what we will do is we will choose a contour with some t very large. Oh, by the way, one point before I continue. So here we have the fundamental domain, along with infinity, is a compact domain. We have an analytic function on a compact domain. It's not going to have infinitely many zeros because the zeros are isolated. Therefore, I can choose a large t such that all the zeros now in the fundamental domain are contained here. Of course, there's this point at infinity which we'll worry about afterwards. Okay. So the contour that we will pick will be of this shape with large t so that all the zeros are now in there. And so this is the contour C. So 1 over 2 pi I integral over the contour of f prime of z over f of z by the usual complex analysis. That's equal to the order of the zeros of f inside the fundamental domain. So I'm making the assumption that there are really no problem points of f on the boundary. Now the horizontal segment, with large t can be mapped to the punctured disk again, can be mapped to the punctured disk about q equals 0 via the usual transformation z goes to e to the 2 pi I z. So this is the trick that I'm using to study the behavior of the function at infinity. You keep using this map q, and so what happens is you see when I'm moving from this point to this point in this direction, you will see that it moves in the counterclockwise direction of 0. So this map is a contour, is a circle around 0 in the clockwise direction. And so we pick up the order of the 0 at infinity. From the vertical as t goes to infinity. For t very large, it doesn't really matter. Fix a t very large, and that's we get this contribution from the top guy. The contribution of the integral along these vertical paths, keeping in mind that f of z plus 1 is equal to f of z, so that the integration on this vertical line and the integration on this vertical line here are the same, except they're going in the opposite directions, therefore they'll cancel each other. Okay, so the vertical line contribution is the vertical line contribution cancel each other. Since f of z plus 1 is equal to f of z. So we only need to consider what's happening on this circular arc. The map that takes this arc, see if I apply the transformation z goes to sz, or minus 1 over z, takes this arc to this arc. Okay, so that's the mapping. So the now on the circular arc, we have we use the following we have the transformation f of 1 minus 1 over z is equal to z to the k f of z. So logarithmic differentiation gives f prime of minus 1 over z over f of minus 1 over z d of minus 1 over z equals k over z plus f prime of z over f of z times dz. So in other words, if I make the change of variable z goes to minus 1 over z on this part, okay, then the integration, so the integration of f prime of minus 1 over z, so I change the variable, and the point is that as I move from here to here, I'm actually moving in the opposite direction from this point in the opposite direction. So a little bit of thought will show you that the integration of this on the first arc, so let's call this C1 and this C2. Yeah, so the point is I choose t sufficiently large so that all the zeros are inside here, except perhaps the 0 at infinity. The mapping q goes to z goes to e to the 2 pi z maps the neighborhood. Remember, the neighborhood of infinity is these neighborhoods when the imaginary part is bigger than t. So that neighborhood, that mapping, it actually maps to an integration in the clockwise direction around the point q equals 0. The point q equals 0 corresponds to the point at infinity, I infinity, under this mapping. So I'm picking up the order of the 0, but with the minus sign. That's what this minus sign is. So it's just basically, it's still classical complex analysis. So all the other zeros are here, and I've now managed to include the contribution of the 0 at infinity by seeing what this top line is doing. Okay? So the only other stuff that's remaining are these zeros that are here. And now to analyze these contribution between on this arc, I'm just making the comment that as I move from this point rho squared to I, the contour under this mapping z goes to minus 1 over z is actually moving in the opposite direction. Okay, so remember now that our integration is in this direction, in this contour, but if I change variable, I'm now moving from here to here, so that part cancels. And I'm going to leave this as a small exercise for maybe you can review it in the afternoon. So these two parts cancel. The only thing that's left is this k over z that you have to kind of integrate around. So the bottom line is the integration of k over z on this arc C2. C2, I should point out, is the integral from rho to I. So it's actually going in the opposite direction. So it should really be minus C2. So in other words, I have to integrate, well, look, you know how to parameter, so you know what these line integrals are. The line integral changes back into a classical integral of ordinary calculus if you just parametrize everything, right? So the parametrization is the parametrization of a circle going from this point rho to I along this arc. And essentially, therefore, you're only going to pick up the contribution of the angle. If it was a full 2 pi I, you'll pick up 2 pi I. But now it's only a part of the thing. So when you do that calculation, it turns out to be an integral k over 2 pi I times pi by 3 to pi by 2 d of e to the I theta over e to the I theta. And it works out to k over 12. So that's basically how you end up getting this. I've made the assumption that there's no problem point at I, there's no problem point at rho squared, and there's no problem point at any of the vertical line integrals that I've got. Now, suppose there was a problem point. So first point, if there was a problem point on this particular vertical line, what we will do is we will deform the contour so as to include it. But then on the other side, we will deform the contour equally at the same point so as to exclude it. So it'll be this kind of path, and that way we get the contribution from this, and if you analyze it, it tallies if you just do this kind of small deformation. If there was a problem at rho squared, you would again deform the contour to do this. And the calculation now is exactly the calculation that we just did when you are not, you're using Cauchy's theorem, but you're not doing the full circle, you're only doing part of the circle. You don't get 2 pi I, but you'll get the angle. If it's a full circle, you'll get 2 pi I, but now you'll only get the angle that's subtended by the particular arc. And that's what accounts for this 1/3 and 1/2. So 1/2 is pretty clear because you will now, if there's a 0 at I, you will go around it, and you're now only going over half of the circle, therefore you should get only half of that thing. Here, the contribution here with this particular arc and this particular arc will pick up 2 1/6, and the 2 1/6 turned out to be the 1/3. Okay, so that's a small, you can tidy it up in the afternoon tutorial. So that's how you get the valence formula. And from this valence formula, we can now deduce many wonderful things. So let me try to give you a sense of how that works. So it's classical complex analysis, nothing fancy like integration on any compact Riemann surface or anything like that, just a classical. So from this formula, the first observation we make is that if k is negative, you have a negative thing here, and these are all positive things, therefore there are no modular forms, so you have mk. The only function that will satisfy everything is 0, the 0 function. For m0, so m0 is just a set of complex numbers. m2 is again the 0 set. Now, let's apply the valence formula to E4 of Z. Remember, E4 is that Eisenstein series of weight 4. So there's nothing interesting happening at 0, and there's nothing interesting happening at 2. The first interesting point is 4. And when we look at 4 here, we put 4 over 12, that's 1/3. The only way you can pick up a 1/3 from the left-hand side is if this guy contributes 1 and everything else is 0. So that's the only way you can have it. So this means that E4 of rho is 0. By the way, I keep telling you rho and rho squared are equivalent, so it doesn't really matter. And E6 of Z is weight 6. And there you have 1/2. And how do you pick up a half? You can only pick it up from here. You can't pick it up in any other way because 2 and 3 are relatively prime. So E6 of I is 0, and that's the only 0. So E4 of Z has no zeros except rho. E6 has no zeros except I in the fundamental domain. All right. And the other thing is, if you have cusp forms, remember a cusp form vanishes at infinity. So if k is less than 12, this number is less than 1. And if I have a modular form which vanishes at infinity, this is going to contribute 1. Therefore, there's no way I can have any cusp form for weight k less than 12. So the first serious thing happens when k equals 12. As I already showed, E4 cubed minus E6 squared is a non-trivial cusp form at that point. So for each of the modular forms of small weight, they're generated by Eisenstein series. So for k equals 4, 6, 8, and 10, they're one-dimensional spaces, and you just have this classical Eisenstein series, which is a basis. And a few interesting facts emerge. For example, you can show E4 squared is equal to E8. And the square of the Eisenstein series is actually E8. And this, when you compare the Q expansions, leads to an interesting formula. The seventh powers of the divisors of n can be written as the sum of the cubes of the divisors of n plus 120 times m equals 1 to n, sigma 3 of m, sigma 3 of n minus m. So these are what are called convolution sums in number theory. So sometimes when you take a function at m and n minus m, it's like a convolution, and you're trying to evaluate this. And one of the interesting things that emerges is that you can derive that actually equals sigma 7 of n minus sigma 3 of n. And I don't know any elementary proof of this fact except this. And there are similar formulas. You can concoct some similar formulas with E4 and E6. E4 is weight 4, E6 is weight 6. Therefore, E4 times E6 has to have weight 10, but it has to be a multiple of E10. And what is it? It's that. And then that gives rise to, again, another convolution identity. So this is some interesting stuff that you can get from low dimensions. But what's interesting is that this Valence formula allows us to give a structure theorem for the space of modular forms. And so I'm going to do that now. So section 4, dimension formula. So as I mentioned, this modular form will play a pivotal role in our analysis. Notice that this is weight 12, and weight 12 means that this now is 1, and we already have a 0. Therefore, there are no further zeros of this cusp form. So delta of z is not 0 for all z in the upper half plane. So that's a very important fact to know, because that's going to allow us to divide by delta of z. So we have a map mk minus 12 to sk. We take a modular form f and you multiply it by delta. And this is a surjective map, because if I take G here and divide by delta, I have a modular form of weight k minus 12. And I can do that because of this comment. Right? Surjective map as delta of z is not 0 for all z. So take any modular form and just divide by delta, and you end up getting that. So in other words, we can apply an inductor procedure to derive the following dimension formulas. The dimension of the space of modular forms, to Z, is equal to k over 12 if k is congruent to 2 mod 4, mod 12, sorry, and k over 12 plus 1 if k is not congruent to 2 mod 12. So I'm going to let you kind of use this observation to derive this. So you can now, you have a kind of a surjective map from here to here, so you can see that it's going to change modulo 12. And how the dimension formula plays out is what you get there. But more is true. What is true is that, in fact, not only do we have this nice formula for dimensions of these modular forms. Remember, I had the structure theory, well, I rubbed it off, but the space of modular forms is equal to the one-dimensional space spanned by the Eisenstein series Ek plus the space of cusp forms. So therefore, the dimension of the space of cusp forms is one less than the space of modular forms. So you can, in fact, also and 0 otherwise. Oops, k over 12 otherwise. And if you look at E4, raise it to the alpha, that's weight 4 alpha. And if you look at E6, raise it to the power beta, that's 6 beta. So if you look at these monomials such that 4 alpha plus 6 beta is equal to k, all of these modular forms are in the space of modular forms of weight k, as alpha and beta run over all the possible non-negative solutions of this thing. And it turns out that, in fact, this is a basis for MK. And the way you prove that is if you try to show, is there a linear dependence relation that you have amongst these things. I'm going to leave that as an exercise, and Karan Dev will cover it in the afternoon. If you have a linear combination of these things that turn out to be 0, then you exploit the fact that E4 of rho is 0 at one place and E6 is at another place, and so somehow you, by an inductive procedure, you can get all the coefficients 0 by keep on. Okay, so I'll leave that as something that you can think about. So here's an explicit basis for the space of modular forms. And now, with this, there's one more exercise which I think I'd like you to do, and that is, it's not totally trivial, by the way, at this point in time, in this stage of the game. E4 cubed minus E6 squared divided by 1728 has integer coefficients. And that requires you to actually look at these Fourier coefficients that I wrote down. I wrote down E4 very, very explicitly and E6 very explicitly. You have to now mess around with those coefficients and make sure that everybody is divisible by 1728. Okay, it's a kind of an interesting exercise in its own right. All right. I've got about 5 minutes left. This lecture compresses 50 years of the theory of modular forms. Final topic for today is the J function. This is probably the function in mathematics which is very ubiquitous. That is, it appears all over the place, and it isn't confined to number theory alone. The J function, J of Z, is simply E4 cubed divided by delta. So E4 cubed is weight 12, and delta is weight 12. And as you know, that delta vanishes at infinity, so there's got to be a pole at infinity. This has a pole at infinity, okay? Moreover, because this is weight 12 and this is weight 12, this has to be weight 0, but it can't be a holomorphic thing. It has a pole, right? So J of AZ plus B over CZ plus D is equal to J of Z for all A, B, C, D in SL2Z. In other words, it's really a function on the fundamental domain, because any 2 points which are equivalent in the fundamental domain have the same value, J value. And that's why this is called the modular invariant. The J function, or sometimes it's called a modular invariant. And if you look at the Q expansion of delta and the Q expansion of E4 and try and work it out, remember the coefficients of delta are these Ramanujan tau function coefficients. So if you work that out in long division, J of Z has a Q expansion. I think I wrote down a few more coefficients in the book, but I write this down because I was actually in Montreal when John Mackay in the 1980s made the observation that, hey, wait a minute, I saw this number 196884 somewhere, and he was a group theorist and he was studying the monster group, and it turns out that 196884 is equal to 196,883 plus 1. Okay? Now that's not the observation he made. The observation he made was this number is the degree of the smallest irreducible representation of the monster group. So he thought there must be some coincidence. It's not just a fluke. There must be some theoretical reason. It's not a coincidence that this is the case. And by golly, he was right. And so this is what has led to what's called moonshine. I don't know if you've heard this. And many people like Borchards, I mean, he got the Fields Medal for explaining that. Why is it that the coefficients of the J function are intimately connected with representations of the monster group, and that they are essentially coming as degrees of representations of monster group? That has a lot to do with the classification of finite simple groups. So this J function, the connections with these coefficients was a 20th century discovery, and the understanding of the J function is central to the classification of finite simple groups. So I just want to put that in front of you. The other thing that before we stop for the day is to mention that the growth of these coefficients, as you can see, it's already pretty big. These coefficients have exponential growth. So let's say I write this as 1 over q plus c of n, q to the n equals 1 to infinity. Then it turns out that c of n is asymptotic to e to the 4 pi root n over square root 2 n to the 3/4. And this was proved by Peterson in 1932 using the Hardy-Ramanujan circle method. As I mentioned in the very first lecture, Hardy and Ramanujan worked on the partition function, and they developed the circle method to study the growth of the partition function. There again you have exponential growth, and so here again you also have exponential growth. So notice that the weight of this function is weight 0, so this is weight 0, but it's not a holomorphic function because there's a pole, and so you have to go to non-holomorphic or meromorphic things in order to study negative weights. You can't get away from that. Once you go to negative weights, it seems that the growth of the Fourier coefficients is exponential, whereas if you look at integral weights, the growth of the Fourier coefficients is polynomial. All right. So maybe I just state one theorem because it's just an immediate consequence of the Valence formula. Let F be the standard fundamental domain. And F prime, the region which we obtain by deleting this vertical line and deleting this arc. Okay, so that's F prime. Be the region obtained by deleting those things. Then the map J from F prime to the complex plane is a bijection. In other words, the J function takes every complex number as a value, and it takes it only once. And the way that's proved is you just have to check when can this equal lambda. F is the standard fundamental domain. F is that's standard fundamental domain. F prime is the region obtained by deleting this vertical line and this arc. And so I'm just taking the map in the fundamental domain Z, and I'm mapping it to J of Z. So the fact is, J of Z takes every complex number exactly once, and only once. If you F prime, sorry, this is F prime, sorry. Yeah, is that what the problem was? Oh, sorry, yeah. F prime. Yeah, but because these guys are equivalent, right? I mean, you can't have that, and this part is equivalent to that part. So you just remove the obvious part, which is not supposed to be included, and then it turns out it's a bijection. And the point of that is to figure out how often do I have E4 cubed divided by delta equal to some lambda. And so the question is, when can I solve this? And that's clear by examining the Valence formula. Maybe Karamdev can do that in a little bit more detail. And just to close, the final comment that I want to make is that the theory of the J function is one of the most important parts of mathematics. And already the simple fact that you have this one-to-one correspondence between elements of this restricted fundamental domain and complex numbers J of Z allows especially arithmeticians and algebraic geometers to try to understand what is exactly the meaning of the fundamental domain. It turns out that the fundamental domain parametrizes all elliptic curves, and for each Z in the fundamental domain you can construct what's called an elliptic curve, and conversely, if you have an elliptic curve over the complex numbers, there's a unique point in the fundamental domain that it corresponds to. So it's kind of what's called a moduli space. And so this is really the tip of the iceberg. It's the beginning of the theory of moduli spaces, which parameterize very interesting arithmetic objects. And the J function is a very important function from that standpoint. It turns out that two elliptic curves corresponding to the points Z1 and Z2 are isomorphic if and only if J of Z equals J of Z1. And that can only happen, that means each one of these things corresponds to a distinct elliptic curve. Okay, so as you can see, it's the beginning of a bigger theory, which I'm just touching very briefly. We will certainly talk about these things at the very end of the course.